Welcome back from the break. So, you know, some of you have done the lab yesterday. We're continuing Shazam. You have this week to finish Shazam. And then we'll begin a couple of new labs starting the following week. I'll also be posting another problem set sometime soon this week. You'll have till a week from Monday to complete that problem set. Okay, so all the due dates got pushed back a week, basically. Okay. Good job on the midterm. I was happy. I was pleased to see how well you all did. So, let me do something here. Let's get back into gear thinking about linear time invariant systems, convolution, the Fourier transform. We've seen that for linear time invariant systems, LTI systems, we've seen that the impulse response characterizes what that system does. So we can say it's a convolution with h of t. And so what comes out is the convolution of these two things. And that we can think about what happens to this signal in the frequency domain, because it's equivalent to say that the Fourier transform of the signal simply gets multiplied at each component by the Fourier transform of the impulse response. So the Fourier transform of the output is just the product. So what that means is we can design what we would call filters, which basically mean we're going to design a linear time invariant system that does what we want. We design what it's going to do in the frequency domain on purpose, for example, to get rid of high frequencies or low frequencies. So in your first lab, I think it was your first one, maybe your second one, you played around with some sounds, and you saw that if you you could keep just part of the frequency domain and listen to it. It would sound one way. You could keep another part and listen to it. It would sound another way. You use this to remove noise from a sound signal. But you're also probably familiar with buttons in your car stereo that say boost the bass or boost the treble. And that's basically doing the following. If here's the frequency, let's say 0. Here's your Fourier transform of your music, let's say. Okay, so this is some audio signal. Well, the bass part is the low frequencies. So maybe you would cut it off at some arbitrary point and say, this part here we'll call bass. Call that bass. And this part up here we'll call treble. And you would have some sort of audio filter that is going to boost one or the other based on your knobs. Okay, is this how we spell bass? Someone smiling at my spelling? Is it B-A-S-S? No, did I spell it right? Huh? Is treble right? The one I thought I'd spell wrong was treble. I spelled bass wrong. Okay, so you're doing some processing to remove or boost part of this. Okay. Now you could design this in a circuit. Maybe some of you have. It's very easy to do a boost of the lower or higher parts with a very simple circuit, basically attenuating the other part. But let's talk about the high-pass filter, well, low-pass filter first. And we're going to start by looking at the ideal low-pass filter. So a low-pass filter should do the following. It has a cutoff frequency FC. And the frequency response of this filter should be the following. Let me do this. Oops. There's F. Now I'm going to do the Fourier transform on both sides here. So it should pass through the signal up to the cutoff frequency and down to negative the cutoff frequency. And the height of this frequency response should be, so this is h of f, should be 1. And if we could design a frequency response for a system, a linear time invariant system that looked like this, then we see that what comes out of our system is simply y of f equals the product, which equals x of f for small f below the cutoff frequency, and 0 for large frequencies. Okay, so this we would call an ideal low-pass filter. All right, now for kicks, let's look at what the time domain, the impulse response of this filter would look like. And this is one we're familiar with. So look in the time domain. Impulse response. So we see that h of f could be written as a rect of f over, now the width of this thing is actually 2 times fc, so f over 2 fc. All right, so we can use our scaling rules, time scaling, in reverse, to say that this is just 2fc sinc of 2fc t. So it's a sinc function that's been scaled appropriately. Let's draw that out here. There's time, and what we have here is something that looks like this. There's 0, and the first crossing happens at 1 over 2fc. So that's at t equals 1 over 2fc. Okay, so we have some sinc, and I guess the scaling of this is 2fc. Okay, so this is the impulse response of our system. So what we're saying is, if we want an ideal low-pass filter, the system has to respond this way to a delta function. Before we go on, can anyone think of why it would be difficult to create such a system? It's not causal, so that's I would say the key reason why this is difficult. Okay, not causal. What's wrong with that?
You have to be influencing your output before you know that you have an impulse.
Yes, so you're not really going to be building non-causal systems. So, okay. Now, there is one trick to, when you go implement a system that maybe that's non-causal, sometimes a time delay will then make it causal. How far do we have to delay this in time to make it causal? Infinity. Okay, so this is a real problem because this goes on forever. All right. But yeah, this is what we're stuck with for the ideal low-pass filter. Okay. we'll come back to that, how to actually implement such a thing. Change color, no. Okay, so how about if we do a high-pass filter? Filter. All right. Here, what we want is everything above a certain frequency, above a cutoff frequency, is passed. Okay. This is H of F for an ideal high-pass filter. How can we go about finding the impulse response of this thing? Oh, I see movement. Okay, it's a little tricky because if you just plug this into the inverse Fourier transform, this is not a energy signal. This is going to have infinite energy. It's not going to integrate well in the inverse Fourier transform. You don't want to just plug this into the integral. But we can do this trick. Here's the trick. In fact, it wouldn't have a inverse Fourier transform if we weren't using delta functions. But the delta functions always, they don't always, but there are salvation for these types of cases where technically you wouldn't have an inverse Fourier transform. Because this has infinite energy. Okay, so here's the trick, though. Let me name these two things different names. I called this one H, let's say, low pass. And this down here, so that's low pass, high pass. Okay, notice that H low pass of F plus H high pass of F equals 1. Okay. Now let's take the Fourier transform of both sides of this. That means that the inverse Fourier transform, H low pass of T plus H high pass of T equals what? And this is a trick question. What does it equal? It's not too much of a trick question, but not 1. We have to do the inverse Fourier transform of 1. This is a function of f. It should maybe say 1 for all f, right? So this is a constant function. And we, by inspection, by memory, by looking at a table, we know what the inverse Fourier transform of this is. It's a delta function. Okay. Again, you're not going to get that by plugging in the integral, but you can get it by experience because we've done. It's going to, yeah, maybe I'll have to switch color schemes. Okay. So delta of t. Again, if you're wondering, where did we get this? You get this, you can get it this way. The Fourier transform of delta t, you can plug that into the integral and find out that it's 1 everywhere. You're not going to be able to plug this in the inverse integral and go this way, but that's what happens with delta functions. They're verifiable one way, usually. Okay, so here's what we have. So then we can say that h high pass of t equals delta of t minus h low pass of t. So this is a funky looking impulse response here. The ideal high pass filter. It's got a delta function here, height 1, and it's got a sink that's negative. Dot, dot, dot. Okay, this is an ideal high-pass filter. Now, you don't really encounter ideal high-pass filters because in reality, you're not looking at signals that, remember, we're going to apply this high-pass filter to some input signals. Well, we're not really going to look at input signals that can have unlimited frequency content. So in reality, you'd say, well, what bandwidth, what's the highest frequencies I expect to ever encounter? Then my ideal high-pass filter only has to be 1 up to that point. That's going to give you a more realistic impulse response. Okay. All right, last one along these lines. Band pass filter. Okay, let's first just do one-sided. There's F, here's 0, and you're going to let frequencies between FL and FH for high and low. Now, this does not correspond to a real-valued system. We know something about real-valued impulse responses. They have to be conjugate symmetric. You would have to have something over here as well if it was real. Let's just do the complex one first. Don't worry about whether signals are real. Okay. So, for convenience, let's define the center frequency, FC equals FL plus FH over 2. This just goes right in the middle. All right, and then we also have the width. I'm going to say FW for width is just FH minus FL. All right, so then we could say what. Then we could define what this bandpass filter is. Let's do this. This, by the way, was H of F, bandpass. Okay, so we could write H is a shifted rect. So it's rect of F over F width. And then shifted by FC. So I'll put that in the numerator. Replace F with F minus FC over FW. Okay. So let me write that here. Scaled F over FW, then shifted F minus FC to replace F. So that means that this is just, that means that H bandpass of T equals, first we'll deal with the scaling. So it's FW sync of FWT. And then we deal with the time shifting, which is just which is just going to be a multiplication by e to the I 2 pi FCT. Good. Okay. So what does this look like? Well, I can't really plot it because it's complex. But it's just a sync multiplied by... All right, I'll change the color scheme to Windows Basic. Okay, so it's just our sync, but it's multiplied by this thing here. Okay, by a complex exponential. So let's look at the two-sided bandpass filter, the real bandpass filter, real valued. Now we could have derived this H bandpass by just integrating this thing. Maybe that would have been easier. I generally tend to try to derive it from known inverse Fourier transforms by just manipulating that. That's a nice technique to do. Okay, so here what we have is two sides. We've got F low and F high, and we've got minus F low minus F high. And what we're going to end up with is, put 0 there, 1, 1. What we're going to end up with is the sum of two things. This bandpass is just going to equal what we had already. And plus another component. W sync. Notice the only difference between this second rect over here is that you have a different center frequency. So this negative FC is right there, right? So the negative I put right there. So that's the only difference between the other part we added. And of course, by Euler's identity, we can simplify this and say that that is 2FW sync of FWT times cosine of 2 pi FCT. Okay, so this we can draw. Now let's assume, for my drawing's sake, that FC is much bigger than this width. So it doesn't look like it here. And I don't want to edit the drawing, but let's, well, I'll just write it here. If FC is much bigger than FW, this is just for the drawing's sake. It looks something like this. So you have your sink, which goes, I'll do a dotted line. Okay, and you have a cosine that goes like this. Whoops. So you see what that product looks like. Okay. So this would be the impulse response for an ideal bandpass filter. This is H bandpass of T. And of course, if this condition wasn't true, it would just be that, I mean, you could end up with a center frequency that's actually smaller than your width. You could get it all the way down to half the width before those rectangles start to overlap. And then the cosine in the sink would be similar frequency, and it would qualitatively look a little different than this. Okay. But there's your ideal bandpass filter. We actually refer to this type of operation as modulation, and I'll talk more about that probably later in this lecture. This is modulation. Okay. So now, before I get to some ideas about how you would actually, we want to talk about filters we can actually implement. But I thought it would be fun to just give you an example of filtering something that we can actually look at. So I put together a little image filtering demo. Let me pull it up. Okay. This is what I wrote in MATLAB. You don't have to completely digest this code, but I'll try to explain a little bit about what I'm doing. Oh, where's the... Okay. So I read in a stock image they have called rice.png. Let's pull up rice here. Just a minute. This is what it looks like. Okay, this is MATLAB provides this. Okay, now what I'm going to do is I'm going to artificially blur it. Okay, it would be nice if I had it really blurred, but for this demo, I'm going to artificially blur it like we have some movement when we took the picture, or there's some blurry lens or something. And I'm doing that with a linear time invariant filter, which is a pretty good model for blur. So here I've constructed a blur matrix. Okay, let me just show you what that is, hold on. Let me just clear this out here. Okay. Blur. Okay, well, it's not very pretty when I don't make it wide. Oh well. So these are numbers. This is a 5 by 5 matrix. There's some zeros. There's some non-zeros. It's one in the middle. I'll show you an image, a grayscale image of this matrix, okay, which is right here. Figure 1. This is what blur looks like, although I put a bunch of zeros around it, just to put it in context, so it's the same size of the image. It's got a blur about that big. So this is the impulse response of the blur. What that means is, this is what I'm imagining the blurry picture of a delta function will look like. What's a two-dimensional Kronecker delta function? In other words, what image am I using as an impulse function here? One pixel right in the middle is white, everything else is black. Okay? And so we're basically assuming that we have some system that would turn that single bright pixel into something like this after blurring it. Okay? And since it's linear time invariant, that tells us everything about what the system's going to do to any image. So we just convolve, and we'll get a blurry image. So here, here's this start. Here's what the image was. Whoops. Here's what the image, I don't want to do that. Okay, here's what it was. And I want to pull up the correct things here. There's the blurred image. Okay. Looks blurry, right? Okay. So now what I want to show you is how I can, if I only had this, and I had some understanding of how the blur happened, how I could process this to try to get something like that back. It's not going to be perfect because I have to do, well, first of all, let me mention what I'm doing here is not very sophisticated. It's not like I've optimized, boy, you can't really read my code very well here, but it's not like I've optimized and made some really sophisticated system. I'm just doing something very simple. I look at what the frequency response is of that blurring function. Okay, so that's here. So this is the Fourier transform, the two-dimensional Fourier transform of that blur matrix. Now notice that it's basically cutting off, it's basically passing a lot of low frequencies here. If the monitor was a little bit better, you'd see that there's actually a little bit of white here and here. Okay, so it's not really just a completely smooth ball. You're just not seeing it very clearly through the projector. But here's the zero frequency. And here are the high frequencies in the vertical direction. Okay, and here are high frequencies in the horizontal direction. And of course, in this is like high frequencies in diagonal directions. Okay, and let's pull up the blur function again so we can kind of understand why we have this slant to it. Okay, you see that the blurring is happening more this way. So that is causing the frequencies in that direction to be removed. Not completely removed, but attenuated. Okay. Whereas the frequencies in this way, yeah, they're also, this is sort of a low-pass filter, but you pass through more frequencies in this direction because it's not blurred so much in that direction. Okay, so blurring is basically removing some of the high-frequency content of our image. Is it clear why I'm saying that? Because convolving with an impulse response is multiplication with the frequency, with the Fourier transform. And this is the magnitude, this is the absolute value of the two-dimensional Fourier transform of that impulse response. Okay, so what I'm going to want to do is I'm going to want to boost up the high frequencies to get them back in the deblurred image. Okay, so I do something that's barely more complicated than simply taking the inverse, 1 over that Fourier transform. I do something slightly different than that here in this line. You don't have to understand this, but I basically add a constant to the denominator is effectively what this is doing, because you don't really want to blow up frequencies that were cut all the way out. You don't want to blow them up really big. You'll get noise would cause problems. Numerical errors would cause problems. And so there's one other problem. And that is that information actually gets lost when it's blurred. So if we look at these two here again, the blurring pushes some of the information off the edges. Okay? When you try, if you want to recover this, you can't get it back exactly, because this doesn't have all the information from this. Some of it got pushed off the edges. So I don't really want to completely try to invert this thing, or it'll look really ugly. All right. So what I end up with is a deblur. Which one is that? It's figure 5. Okay, so this is the impulse response of my deblur function. Looks really weird. You can tell it kind of has high frequency content, but let's compare it to my blur impulse response. Whoops. So here's the blur. Gosh. There's the blur, and here's the deblur. Okay, notice one thing. The deblur looks much further out in the image when it's trying to reconstruct a single point. Okay, this is a much wider sort of impulse response. Just to check that this really sort of inverts that thing, what can I do? I can convolve this with this, and then what should I get back if it did a good job of inverting? The impulse function, because this is the output when the input's a single pixel. So if I deblur this image, I should get back my single pixel, right? Let's see what I get when I convolve those two things. Close. Now, if you looked on a better monitor here, you'd see there's actually a lot of little artifacts around here. It's not exactly just 1 pixel, but it's close. Okay, so that's good so far. So now let's. I'm going to pull up the blurred image, and I'm going to pull up the deblurred image, and we'll compare. So here is, all I did here was convolve this with that deblurring impulse response to get this. Okay, so what's good and bad about this? What? Yeah, what's this coming from? Yeah, this edge effect. The deblur is trying to deblur these points, which would require information out here that it's not used, so it's messing up. So if I really was going to make a commercial product, I would be more careful about how I do it. This was done very quickly in MATLAB. But did it work somewhat? What? It did? Yeah, this is definitely a lot sharper than this. I'm glad to hear it. So here's the here's the original blurry and then deblurred. And you know, it qualitatively is it's a lot more like this than like this, right? Yeah.
Why is there no edge effects on
At least there should be some, but you're not really noticing it, and I think it has a lot to do with the fact the impulse response was much more vertical than horizontal for the inverse. Yeah, that's the only explanation I have. If we look back at the impulse response here, which was this one, nope. Close that. This one. That's Fourier transform. Which one is it? 5? There. It's much taller than it is wide, and so it's that causes more rippling in that direction. What? The inverse of, you mean like a matrix inverse? The matrix inverse would not do it. Yeah. Because we're not doing a matrix multiply. We're doing a convolution. So if it had been a matrix multiply with that thing, then we'd do matrix inverse. But it's a convolution, so we have to do the inverse of convolution. And an inverse of convolution is better understood in the frequency domain. Because then it's literally just 1 over the frequency response at each frequency. Okay. Any questions about this? We'll go back to talking about. Good. Let me show you in here, but since you can't read this, I'll post this online. But it's all this line right here. It's all Yeah, it's all this line. All I'm doing is I take my blur, in this line up here, I take the Fourier transform of this blur matrix. And then the next line that does the entire magic, it just, I'm just basically taking 1 divided by that Fourier transform. So 1 over the Fourier transform of the blur matrix should be the Fourier transform of the de-blur matrix. Because what you want is when you multiply them together, they get 1, right? So I just basically take an FFT, take 1 over each value, and then take an inverse FFT. And if you do that, you'll see much more artifacts than we see in my example. It would actually look a little bit hideous, and you'd be like, this doesn't work at all. Because of these, you're amplifying some frequencies a whole lot. So the only extra part I did there was I basically cut it off and said, don't amplify it beyond a certain amount. And then you get this type of thing. So it's a high-pass filter. A sharpening process is high-pass filtering your signal because the blurring was low-pass filtering. Okay. So now let's let's talk about this. So if we want to talk about how do we actually implement a filter, maybe I should say that first. So say we have some filter design we want. We want to boost the bass of some signal. We want to sharpen an image. Want to do something. We know what we want it to do in the frequency domain. How do we actually implement it? And there's many ways to go about this. First of all, I'll say if it's not real time, then you have a lot of choices. In other words, if you have a recording of your audio and you just want to go make it sound different, and save it as a new audio recording, then you can do all sorts of things. Causality is not an issue. You could use the FFT. I'll say carefully. There are ways to make mistakes this way, but you could use the FFT and just rescale things. You could design a non-causal filter. If you think about that image filter that we used, that was non-causal. If you want to define causality as everything being on the right of the center, well, my impulse response was on both directions. It didn't matter because the causality of images is meaningless, right? Okay, so, but if it's real time, then we have some issues. And so, by that I mean if you have a, let's say someone's singing in a concert and you want to apply some sort of audio effect to their singing. So their voice goes in the microphone, it's going to come out the speakers, and you want to have it processed. Well, now you have to be causal. So how do you implement some sort of filter there? And here's one way to do it. Is a finite impulse response, which we say FIR filter. And what this means, this isn't the only way. We could do, this is one way. But this way will be the easiest to understand, so we'll go ahead and talk about this. So you're going to have, it's discrete time. Oops. and h of n equals is non-zero only on n in some set. Let's say 0 to capital N. Okay, so so what we mean by this is your filter has finite width. So it's like you can design whatever you want, but it has to stop eventually. Start at time 0 and stop at time n. Okay. So let's look at trying some ways of creating, say, a low-pass filter with a finite impulse response. Okay. Well, we're in discrete time now, and I will talk a little bit more, probably not this lecture, on the differences between discrete time and continuous time. This will be a major topic of next week's lectures in sampling. But since we're in discrete time, let's at least verify that the discrete time ideal FIR filter, what would that be? So, sorry, the discrete time ideal low-pass filter. Forget FIR. Let me put that in another color here. So in the frequency domain, again, we would like it to be like this, up to some sampling frequency. But in discrete time, you have to remember that everything is periodic with period a half. So in other words, the Fourier transform of any discrete time signal is going to repeat. It would go like this. That's just a property of aliasing. So we only really have to draw what it is in the first range, frequencies up to a half. So we have some cutoff frequency, FC less than a half. Okay? But you'll realize that when you do the integral for the inverse Fourier transform, discrete time, you only integrate from negative half to a half, so these don't affect the integral. So if we do the inverse Fourier transform, we actually get exactly the same sinc function back, except for its discrete time. So it's going to be something like this. And so it's just it's like a sampled sinc function. Okay, so that was simple enough. This is the ideal discrete time low-pass filter. Now, this isn't always going to be true. If you do it the opposite way, if you say, well, what if I took a rect in discrete time and took the Fourier transform of a rect? Turns out you don't get sinc. Well, you can't get sinc, right? Because whatever you get back here has to be periodic. Right? And the Fourier transform of any discrete time signal is periodic. So it's not always going to be the case that you get the same pair as you got in continuous time. You actually get, if you have a rect in time, in discrete time, you actually get what people refer to as the discrete time sinc. It's, instead of a sine x over x, It's a sine x over sine x of different frequencies. Okay, so this is something to be careful about. It wasn't just for fun that we verify this, but at least the low-pass filter is exactly like we want it, because it's going to be integral from negative half to half of rect f over 2fc e to the I 2 pi f t df. And it turns out that that's exactly equal to negative infinity to infinity of that same rect, assuming this property, that fc was less than half. And it'll be so it's exactly the same inverse formula that we would have got if it was continuous time. Okay. So we have the same problem, though. This goes on in both directions infinitely. How do we actually implement it? Well, here's one idea. Let's window the ideal impulse response. So what that means is we take our ideal one, which was like this, and we just take a certain window of it and we ignore the rest. We say, well, it's small enough outside there that it's not going to affect too much if we get rid of it. So now we have something finite. Now it's still non-causal because it's 0 here, goes back. So let's say we window up to capital N and minus capital N. Well, now we should delay it to make it causal. And then that's going to, so that means that we have that same thing there. But it now goes from 0 to 2n. Okay, so we have something that we might use as a finite impulse response and hope that it does low-pass filtering. Let's figure out what it really is going to do. Because we started with a low-pass filter and then we changed it, right? So the effect of windowing is that we now have, we had our ideal low-pass filter, h of n, and we multiplied it by, in this case, a rect. So this up here was a rect, right? That blue shape is a rect. So what we end up with is h of n times a rect. And so what is that actually going to do in frequency? So it's rect of n over 2n. Now, multiplication in time, what is that in frequency? Convolution. Okay. Now, that property we derived for continuous time. The property carries over for discrete time with one little change. It's what we call circular convolution. But for now, don't worry about that. It's not going to be very different. So this here, in general, so what we have then is we have our ideal low-pass filter, which was like this, and it's going to be convolved, say circular convolution, with the Fourier transform of our window. If it's a rect, we know that's going to be like something like a sinc, this discrete time sinc. Okay, so, but in general, this could be we could use a different window other than a rect up here. What's the result of this convolution look like? So this is going to end up looking something like this. And there's our cutoff frequency from before. So by changing our low-pass filter to cut off the ends of it, something you might do without even thinking about it in MATLAB, you might say, oh, I'm going to apply some filter, but I only can have finite length vectors, so I'm just going to cut off the ends. Well, now we know what that actually is doing to your filter. Rather than giving you the ideal filter response that you thought you were designing, you actually have that ideal filter response convolved with the Fourier transform of your window. Okay, and for a rectangular window, that's going to be this discrete sink. So you're going to get something like this. It's no longer ideal, but it's still a low-pass filter. Has a little bit of rippling in the, so they call this, so it has a little bit of rippling in the part that you were trying to let through uniformly. And it doesn't cut everything off at the high frequencies, and it has sort of a transition period. Okay? So if you studied DSP more, you would learn that there's other ways of designing different windows here. There are different window designs. So rect is the most natural one if you're not, for example, you would use a rectangular window if you didn't think about what it was doing. You just cut off the ends. That's a rectangular window. But you could also use windows that kind of weight the middle more than the edges. Okay? There's a whole lot of different window designs, and they have different effects on the frequency response. Okay. Now there's one more thing we did. We not only cut off the edges, but we delayed the whole thing. Okay, so that means the output is going to have a delay as well. So for now, that's all. Okay, now let's, I guess, say, how would we actually implement this FAR filter? So let's say we've designed an impulse response that's finite in length. How do we actually implement this? We have some circuit board that is taking samples of a signal. What do we do to implement a FIR filter? Yeah. Exactly. So let's say, first of all, that we have to store the last 2n samples. So we need at least memory to store 2n samples. And we'll just write over the old ones with the new ones that come in. So. And then if we write out what the convolution is that we need to calculate, y of n is sum from k equals negative infinity to infinity of h k x n minus k. But since h is 0 outside of a certain range, this is really k equals 0 to 2n, h of k x n minus 2k. Whoops, n minus k. So we've stored these in memory. We just do this sum, and we spit it out. Okay, so there we could actually, in real time, implement this filter digitally. So this is what's called DSP. DSP. Digital Signal Processing. And there's one technique for designing an implementation of DSP. Now there are other filter design techniques. So this one that I mentioned here is you design your ideal filter, and then you window it to make it implementable. Okay. You window it to make it implementable, and you say, well, that window destroyed my filter to some degree, but I could find a different window that maybe is a little more favorable in the frequency domain, and then I just delay it, and I have a causal FIR filter. Okay, there are other more direct approaches to designing. So you can directly optimize. So given the length of your FIR filter and a desired frequency response, you can find an FIR filter that matches it as closely as possible, for example. And on top of that, there are a lot of analytic designs that have been developed over the years. I'll say well-known designs. Like Butterworth filters, elliptical. And so if you study DSP further, you would learn about these interesting designs that try to optimize the flatness of, let's say, a low-pass filter within the frequency range and the quickness with which it drops to zero outside of the frequency range. And so a lot of work has been done here. But you see that it's not as simple as just picking what you want, because if you just pick the frequency response that you want, you're going to end up with something non-causal and not finite impulse response. Okay, let's take a break, a couple minutes. Mm-hmm.
Why is this line, the blue line? Why is this convolution? I thought convolution was in the frequency domain because we were multiplying them in the time domain.
Oh, yeah. Okay, I think you're thinking about the multiplication going on here.
Yeah,
that's true. I'm not talking about that multiplication on that line. So what I'm talking about down here is. Yeah, it's confusing because I'm calling that H. I'm talking about after you've finished your design. So here we were looking at what happens when you came up with some.
Yeah.
Once you've finished that design and that's what it does in the frequency domain, then how you actually go and implement it, because what we want is now to do a convolution with the input signal. So what we're going to do is we're going to calculate the output as a convolution of our final design with the input signal. So this is not meant to be that window.
But this K is in the is this in the frequency? Is this in the time or the frequency?
It's in time.
Okay, so we're taking the impulse response, which is not this, it's the other one.
Yeah.
We're taking this.
We're taking the windowed thing.
H of n, right?
Yes.
And then that.
So this thing here.
Yeah.
There's H of n, and then it actually so then to actually implement it, this should
And
be
then you
involved with any
convolve it
input.
what's coming in.
Yes.
Okay.
Yes, exactly. Uh-huh.
Just to check that I actually got it.
Yeah.
So that like the square with the squiggles on it, like that y of n. If you put it in the frequency domain, it's going to be that square with squiggles on it times the Fourier transform of the input.
Yes.
Okay.
Exactly.
I tried it too, it didn't work that well. I remember there's one song that's not. Yeah. Okay, so a mathematician and a physicist and a philosopher were having a discussion about what the greatest invention of mankind is. And the the physicist said it was fire because that gave mankind the control over the elements. And the mathematician said it was the alphabet because that gave mankind control over symbols. And the philosopher said it was a thermos. And they asked, well, why is it the thermos? And he said, well, the thermos keeps hot liquids hot in the winter and cold liquids cold in the summer. And they said, yes, so what? And the philosopher said, think about it. That little bottle, how does it know? Okay, so I have another filtering demonstration that I put together. Let me open it up here. So let's see. Okay. So this is going to take a little bit of explanation. This is so what I'm doing here is I'm going to filter voice. I have several recordings of voice. Let me start at the beginning here. I recorded myself, and I apologize. The recordings are actually really poor quality when I play them to you. Hopefully that'll work. There's a lot of just fuzz noise because I recorded it on a microphone that didn't have very much volume, so you just get a bunch of noise. But
Anyway, the 4 recordings I'm showing here in the frequency domain are ah, and then ah again at a higher pitch, and then E at a higher pitch. Okay, those sounds, very short recordings. Just to see what is the difference between sounds that are the same pitch. For example, this E sound and that ah sound are both set at the same pitch, but yet you can hear the difference. So let's look at what the difference is. Some of you, who's played around with this, looked at recordings of sound of different vowels, for example. Has anyone done that? A little bit here. It's a fun thing to do, and you say, how can I tell the difference here? And a lot of it has to do with the magnitude of the frequency response. So these 2 functions, which you can't see much of because the frequencies go up to a very high. I'm going up to 20 kilohertz in frequency. I didn't do an FFT shift. So this is the low frequencies, and then before it even gets up to a kilohertz, it's basically died off mostly. So we're going to have to rescale if we want to see anything interesting here. Okay, so here I've just rescaled and said, let's ignore the really high frequency stuff. Let's just look from 0 to 4 kilohertz. And what do these sounds look like in the frequency domain? Okay, you hopefully notice one defining feature already. They've got a bunch of these peaks and nothing in between. Okay, what is it about voice that makes that happen? I mean, this is a Fourier transform that has values very densely along this line, but they're all just very small except right at these peaks. Why is that? So voice, like many signals, is periodic or nearly periodic. If you hold the tone and you look at it, a recording of it, it'll look the same repeated many times. Okay, and something we'll notice about periodic signals. Again, this will be topic this week. You're not expected necessarily to completely understand this demonstration, but periodic signals have harmonic frequencies, and all of their content is at multiples of the base frequency. Okay, the period of the signal. So you see here automatically these basically the fundamental period is pretty much the same. And yet in these ones, okay, there's something going on here, but really this is the fundamental period, and these are all multiples of it. And it's higher than that one. So here is me saying, ah, instead of ah. So I changed my pitch, right? Okay, and this is E, and that's E. Okay, so now what we want to notice, though, is how are the ahs similar and the E's similar to each other? Because, when I say ah with a different pitch, you still know it's an ah. So what is it that's similar about it? And really that has to do with the shape, the envelope that these harmonics have. There's a way of modeling the voice as your vocal cords are the source of the voice, and then they pass through your throat and your mouth, which is an LTI system. Okay, and the vocal cords pretty much are just creating a very sharp periodic pattern. That's creating a bunch of these frequencies evenly spaced, but then the shape you put your mouth in is going to cause an impulse response of the throat and mouth, which means there's a frequency response of the throat and mouth that are going to shape how large these harmonics are. So you really have a product going on here. You have a product between the source, which is just gives you a bunch of these peaks at these frequencies, and the impulse response, or the frequency response of the throat and mouth. And that is what's in common between both times I say ah, or ah. I'm saying it, I'm keeping my throat and mouth the same. I'm just changing the excitation, the impulse response. So there should be some sort of envelope that these both have in common? Now, it's not going to be perfect, but it's definitely different than the envelope you see for the E sound. The E sound makes the harmonics at the very low frequencies pronounced and gets rid of them up here. Okay, it doesn't have a lot of harmonics up here in both cases. So let's look at this a little more carefully. I have another plot. So now what I've done is the same thing, but I'm looking at the log magnitude rather than the magnitude. Okay, so in other words, I'm just taking the log of the vertical axis, and I get these. Now, by doing that, this is a very common technique in speech processing, where you say, if I just, in this log plot, if I just try to smooth out this plot, then I can somewhat claim that I'm separating the excitation part from the general shape, where the general shape, people say, is coming from the throat and the mouth, and the excitation is coming from your pitch. So this is a trick people use to try to remove the tone, remove the pitch of your voice from the actual throat and mouth frequency response of your voice. I don't love this trick, but it's very common. It's called Kestrel coefficients and so forth. If you work in speech, you'll come across this. And really what they're trying to do is they're trying to pull out the envelope of these harmonics. And this just turns out to be a very brute force simple way to do it, where you just do a low-pass filter of the log of the spectrum. Okay, but look at what happens when I do that. So this red represents the low-pass filtering. Okay, and the red then is going to be interpreted as the frequency response of my mouth and throat when I said that sound. And so what we'd like is for the red curve of both E recordings to look the same, because I kept my mouth and throat the same in both of these. So even though the pitches are different, and this is clearly different, but once I took a log and I smoothed it, we'd like for it to be, this red curve to be the same in both cases, so we can say that characterizes what I was actually trying to say. And then these two, we'd like them to be the same as well. So let me just plot those red things side by side. Whoops. Okay, and I changed their color. So here are my 4 throat mouth impulse responses that I've pulled out of those recordings. Okay. Now I've color coded them here. 2 of them are from the ah sound. Remember, ah 2 is a higher pitched ah. And you see that even though they're not exactly identical, the 2 ahs, this blue and this green, they do match up pretty well. I mean, they have some spots where they're not matching up, but in comparison to the red and blue, which is the E sound, they definitely pair off. The ahs look similar and the E's look similar. So I could claim at least somewhat that, yes, I have pulled out something that identifies what the throat and mouth were trying to do to the signal. Okay. Now, I said this is a filtering example because, for fun, I went ahead and said, well, can I build a filter that will change the E sound to ah? Okay. How might I do that? How would I make a linear time invariant system that's going to change an E to an ah from this data here? What? Frequency shift? Oh, something like that might work, but that wouldn't be linear time invariant. Let's just stick with a linear time invariant system, which means all it can really do is give me a frequency response. My E should come in, should hit my linear time invariant system, and out should come ah sound. So how do I design the impulse response? Yeah?
Like, you know, the response frequency, you can undo, E is coming in, undo the E impulse response, and then
Do the ah. Exactly, which ends up being a ratio. I just divide the ah divided by the E frequency responses, and that's the frequency response that I want. So this is on a log scale, so it's the difference between these. I average the green and the blue to get one estimate. Average the light blue and the red together. Okay, take a difference, take the exponent. So basically I'm taking a ratio, and now I get a frequency response. It's not going to be perfect, but I'll play it for you. So this is the frequency response of my E to ah filter. Okay. So I cut it off here because here you're not going to get a very good filter design up there. So it's going to be low pass filtered. Okay. And here's the impulse response of my E to ah filter and my ah to E filter. Okay. Now, if I was really good at, hypothetically, I could make a box, an echo chamber, that gives me this impulse response. Okay, design it all carefully to get so that when I tap the input, this thing comes out. If I could do that, that would be an LTI filter that's designed to do this. Then I'd speak in it E, and that would come ah. Now you can do something like that with your hand. It's not an E to ah filter. It's more like an E to O filter or something. If you say E, right, or E, I don't know. You can play around with that. Okay, so yes. So, but I can't actually play from this computer because this room is broken. So I have to play from. I have to play from here. Let's see if I can do it. Again, this is done very crudely. I didn't do a lot of optimizing, and you can play around and make it much better. This was just from like one recording, or 2 recordings of E and 2 recordings of ah. Let's see. Hold on. What? All right, I'm having trouble. What? Well, this is not good. It plays from my laptop, but I thought this would play. What? Let me try again. Wow, what is going on? Well, that's a bummer. Attempt to reference field of non-structural array. Don't think it's going to work. You can run it on your own. I'll put it online. Sorry.